We're going to have a look at some capacitor questions for A-level physics paper 2. So we're going to do some multiple choice questions, but those, just because they're 1 mark doesn't mean they can't come up as a longer mark question on another part of the paper. And usually there's a fair bit of knowledge to unpack in each one. So we're going to start off with this question here. This question is about time constant, and it's one of the easier type of questions you could get regarding capacitors. The question says, what is the time constant for the circuit? So time constant, we need to know what that definition is the time taken for the voltage or the charge or the current of a discharging capacitor, time taken to fall to 37% or 0.37 of its original or its initial value. That number comes from, if we look at our capacitor equations, so all of the capacitor decay equations look in a similar format, something like this. The idea is that if I do e to the power minus 1, that's when the time taken is equal to RC. So time taken being equal to RC means those two are going to be the same. E to the power minus 1 is around about sort of 0.37, around 0.37, so that's why it's that number there. So all you've got to do for this question is have a look at our graph really. Quick calculation first, it starts at 0.1, so we've got to go to 0.037. So the grids aren't actually amazing here, but 0.037 out of all the options is roughly about here. So let's go down after we found it, and we should find that that comes down to about 5 seconds, which is part C here. This question over here we've got is about a capacitor discharging, but this time we're not given a graph or anything like that. We've got to work out the time constant of the circuit when it loses 50% of its charge in 10 seconds. So let's use our exponential decay equation to help us. So V equals V naught E minus T over RC. This time we're talking about charge, so I'm going to make it Q, although it really doesn't matter whichever one we use in this question. Now for this question here, it tells us it loses 50%, so we need to rearrange it so it's a ratio. So Q over Q naught equals e to the minus T over RC. Now we're going to try and find out what the time constant is, which is this bit here, which means we need to take the natural log of both sides. So I'm going to natural log of Q over Q naught, that gets rid of the E here, and it equals minus T over RC. We can basically ignore the minus sign here in our derivation, and we can just find out what this is. So now I've got ln, and this is 50%, so that's the same thing as the charge now being 50% of the original. That's the same as writing 0.5 or 1 over 2 equals to T over RC. We're trying to find what RC is, so let's do RC, that's the time constant, is equal to T, the time taken, over 0.5. Now the time taken in this question is 10 seconds up here, so I'm just going to replace this with 10. If we put this into our equation, we should get a value of minus 14.4, which, bear in mind, this whole thing is minus and minus, so therefore it's minus 14.4. When working out RC just becomes 14.4, which gives us option C in this question. Using the exponential decay equation in questions like this that are only 1 mark can seem really long, but it is really worth it. If you get really good and practice at how to do this, I reckon you could do it in under a minute. So in this question, we've got a PD, it decreases from 6 to 1.5 volts. It happens in 92 seconds. We're trying to find the resistance when we know the capacitance. So we've actually got all these terms in our equation already. So let's just sub those in now. So it's discharging. So it's 1.5 is the voltage at the end. 6 is what it is at the start, times by E to the power minus 92 over C, we know is 220 microfarads times by R. So what we're going to do, we need to get that R value down, so we're going to take natural logs of both sides. So natural log 1.5 over 6, and that equals minus, and this all comes down here. So we've got 92 divided by the value for our capacitor times by the resistor value. So let's work out what the natural log of this is and rearrange. I might just do this step first actually. So we've got R comes over to this side here, and we've got over on this side 92 divided by 220 microfarads times by our fraction ln 1.5 over 6. So if you put these values all in, we get a value of, so it's minus over a minus, this all comes to minus 301, 654, etc., which it rounds to 300 kilo ohms. That's option B. For this question about energy stored in a capacitor, there are a few different equations we can use. You have to be able to use the right one. So we've got the energy stored in your equation sheet is either half QV, or it's half CV squared, or it's half Q squared over the capacitance. Now in this question, I hope it's obvious, we can't use this one, and we've got to use one of these because it's a constant capacitance and we get given it in the question. The question is, can we find the voltage or can we find the charge? Now we hopefully can see we've got time taken, we've got a current here. So using Q equals I times T, we can find the charge. And it says the current is constant, so that means the total charge is going to go up linearly, so total charge we can find just using this equation here. So let's work out what our charge is first. So IT equals 10 times 10 to the minus 6 times by the time taken, which is 20, which is going to give us a value of, so this is 2 times 10 to the power minus 4 coulombs. Then let's put it into this equation here. So we've got the energy transferred is half times by, make sure you square our charge up here, divided by the capacitance, which is 1 microfarad. So that's 1 times 10 to the minus 6. Remember to halve it as well, and we get an answer of option C, which is 0.02 joules. For questions like this, it might take a little bit of figuring out what actually you're given in the question and what you're trying to find. So we've got the value of capacitance for the capacitor. We've got potential difference when it's fully charged, so that's V0. We've got a constant current, which is using, so 1 microamp, and it says it can be used until the PD across it falls by 10%. And how long, so time taken, is what we're using for it, but time it must be recharged, i.e. by the time it's fallen by 10%. So let's use our exponential equation to see what we can find out, what we're given and what we're trying to get. So when it asks for how long, we're looking for the time taken. We've got the V0, so the initial charge when it's fully charged. We have the capacitance, but it doesn't look like at the minute we have much else we can actually use. We also don't have the value is at the end. However, we do have the fraction it falls by, the ratio it falls by. So it falls by 10%. So what that means is, anytime you see a ratio or fraction like that, we can basically say that this then has to be 90% or 0.9. So I'm just going to rewrite this initially so we can sort of use that to help us out. So we know this here is going to be equal to 0.9 because it's fallen by 10%, not to 10%. So we also don't have our resistance for this question. We don't have the time constant, but we can work out our resistance. So going down here again, if we've got a constant current of 1 microamp, and we know that there was an initial value of 5 volts when it's fully charged, we can use that to work out the resistance using Ohm's law, R equals V over I. So plugging those values in, we've got 5 volts divided by 1 times 10 to the minus 6, which means our resistance value is going to be 5 million, or 5 times 10 to the power 6 ohms. So let's plug these numbers in, and I'm going to take logs of both sides because hopefully it's obvious. To find T, T, we are going to have to bring this down. So we said V over V0 was 0.9, so ln 0.9 equals, now I've got minus the time taken, the thing I'm trying to find, divided by RC. So R we said was 5 times 10 to the 6. And C, the capacitance, is given up in the top of the question, 2 times 10 to the power minus 3. So getting these values onto this side, we have a final calculation which ends up being just over 1,000 seconds, which is going to be option D for this question. That's the time taken before it needs to be recharged. This question looks pretty horrible because there's no numbers in it, but honestly, once you get your head around what a time constant is, it becomes a little bit easier. So we've got an initial potential difference, V0 discharges through a time constant, capital T, tells us base of natural logs is E, so basically we're using something like this equation here to help us. And it says, what's the potential difference after time t? So this time, instead of this little equation here, we're going to put the capital T here, because it tells us in this question time constant is equal to, and after time t, time constant, we should know it's gone down to 37% of its initial value, or its original value, when it's fully charged. So when that happens, what it means is that these two are going to be equal to each other. So when the time taken is equal to one time constant, we can then simplify this down and say actually it's V0 times E, to the power minus 1, because those two things are equal to each other, so therefore this cancels down to minus 1. Now when that happens, e to the minus 1, it says what is the potential difference, basically what are we looking for here. Another way of rewriting this, instead of e to the minus 1, anything to the minus 1 is saying v naught over e. So in this case, it will be option B for the answer for this question. This should be one of the nicer questions on your multiple choice section for paper 2. We've got an uncharged capacitor. It's got a capacitance of 4.7 nanofarads, so times 10 to the minus 9 farads, and the potential difference is 1.5 volts. How many electrons are there that are transferred? So to find out how many electrons, we need to find the total charge and then divide by the charge on one electron. So from our equation sheet, Q equals V times C. So we're going to multiply those two numbers together and use that to find out what the total charge is, and then figure out the charge, how many electrons there are. So this gives us a total charge of 7.05 times 10 to the minus 9. And then we know total charge is equal to the number of electrons times by the charge on each electron. So to find the number of electrons, what we need to do is number of electrons, divide that number there, so the total charge 7.05 times 10 to the minus 9, divide by the charge on 1, and that will give us a value that is going to round to option C, so 4.406 times 10 to the power 10 electrons. This question we've got, it really tests your understanding of what a capacitor is. So we've got a few different options for what the answer is. If we have basically a parallel plate capacitor and a resistor, you move the plates further apart. So we start off with them about this distance apart, and we start to move them further apart. So I'm going to eliminate a couple of these first to make it a bit easier for us. Capacitance of a capacitor, that should be one we can use kind of quite easily with our equation sheet. So we've got capacitance is proportional to area, it's inversely proportional to distance. So if I increase that, that's going down, so it's definitely not D. A decrease in potential difference across the plates, it's still connected to the battery. So if it's still connected to the battery, this one can't be the case. The voltage is going to stay the same regardless of the plates across the capacitor. Then we've got energy stored and we've got charge. Okay, so I'm going to talk about charge. When you've got a capacitor, the charge builds up on one plate in a negative. One plate becomes negative, the other plate becomes positive due to absence of electrons that are leaving the capacitor. Now, if you start moving them further apart, one of the reasons why electrons start building up on the plate, reason one is that they're repelled away from the negative end of the battery, so up here. Another reason why they get repelled from this plate, one of the reasons is because they're attracted down to the positive end of the battery. The other reason is they're repelled away. They experience a repulsive force from the electrons here. So if you're an electron here, you're going to sort of have a repulsive force from over here. If you start increasing that distance away, there's going to be less of a repulsive force. So therefore, a few electrons might just start hanging around on this plate instead of being repelled away. So it's actually going to decrease the charge that's held on the plates. So that will be option C. In this question, we've got a question all about the value of ratios between voltages across two capacitors. And you really got to read this one carefully. Two capacitors are 1,000 microfarads and 10 microfarads. They're charged, so they have the same energy stored. The PD across one of them is V1, the other one is V2. So if we're talking about energy stored and PD, one of the main equations we could use, because they've got constant capacitance, is this one here. So half times by C times by V squared. Ratio between these two squared, that's another hint that we're going to be able to use these as well. So we can basically ignore the half in this question. Essentially, we're saying energy proportional to CV squared for each one. So when we're trying to find the ratios, we know that they have the same energy stored. So what we're going to do is have the same energy stored. So this ratio here is going to be 1. Okay, so E1 over E2 is going to be 1. Now for that to be the case, we've got capacitance 1 is of 1,000 times bigger than capacitance 2. So 1,000 times by V1 squared divided by it's 10 microfarads. So therefore it's going to be 10 times by V2 squared. So let's start to, what they're looking for in this question is this ratio here. So let's sort of extract that out and say we say that the energy stored of 1 divided by energy stored of 2 is the same. So therefore we can say that that ratio has to equal 1. So we can then just replace that on our left-hand side. So we're left now with 1,000 here and 10 here, times by the ratio. We can just put these all in one big bracket and square it. So I've got V2 V1 over V2 all squared. So if we're going to find this ratio, let's then figure out, well, what is this going to be equal to? So if I was to basically just get this by itself on one side of the equation, I can put my 10 over here, I can put my 1000 over here, which is going to cancel down to 1 over 100 is going to be equal to V1 over V2 squared, which means it's option B for this question. Next, we've got a question all about the orientation of polar molecules. So polar molecules, dielectrics and capacitors can be a topic that's really tricky to get your head around. So the idea is, in between a capacitor's plates, if you have air, it's a relatively good insulator, the capacitor will work. However, we can make it better by inserting what's known as a dielectric. Now, the best dielectrics have polar molecules in them, which you'll know more about if you do chemistry A-level, but polar molecules, for the sake of physics A-level, essentially have a positive end and a negative end, and they always line up with the electric field that's being applied. So with the electric field that's being applied, let's just say it's going to be positive here, negative here, so the electric field is going to go in this direction across the plate from one to another. So being the case, that's going to mean that the polar molecules are going to have their positive end line up next to the negative end, and it means that they're going to have their negative end, the left-hand side in this case, lining up against the positive end of the capacitor. So like this. Now, if we translate this question here, we've got an electric field, we've got it moving from positive to negative. So which way are these going to line up? So if you sort of translate my drawing over here, we're actually going to have the positive end going to have the negative end of the polar molecule line up next to it. So it's option A for this question. Some multiple choice questions you get, there's not really any shortcuts. This is one of them. Basically, which statement is correct? You've got a bunch of values given to you. My way of doing it is just you have to go through each one at a time and figure out which one's correct. There's none that are obviously incorrect. You can't really narrow your choices down with questions like this. So let's deal with A first of all. We're trying to find the time constant, which is going to be the resistance times by the capacitance. So let's just work that out straight away. So resistance in this question is 500 kilo ohms, and the capacitance is 30 microfarads. And so if we multiply those two things together, we are going to get obviously something that's going to be close to 15. But if we times them together, we're going to get not 15 milliseconds, we are going to get 15 seconds. So that's not going to be answer A. Next one, Q0 is what we're looking for, the initial charge. How would we find that? Well, we've got the capacitance, which is constant, and we've got the EMF, which is basically the initial charge, or the charge when it's when it's fully charged. So let's deal with B. Is Q0 going to be equal to, so the initial voltage times by the capacitance, that going to equal 12 microcoulombs. So if we do 30 times 10 to the minus 6 times by 4, we don't get 12 microcoulombs, we actually get 1.2 times 10 to the minus 4 coulombs, or that's actually 120 microcoulombs, so it's not B. For option C, let's see what we can do. We're trying to find the time taken. So time taken, one time constant, the PD will be 1.5. It starts at 4 volts. So we know that time constant, after one time constant, it falls down to 37% of its initial value, or its fully charged value. So basically, if we do 37% or 0.37 of the initial PD, so 0.37 times by 4, that will actually give us 1.48, which will round to what the value is here, 1.5. So therefore the answer is option C for this question. This question is all about the designs of a capacitor. What happens if you increase the dimensions in a certain way to the overall capacitance? So the equation we're going to keep an eye on is this one here. So we've got the relative permittivity times by the permittivity of free space divided by the distance, or the gap between the plates, D. So when we're trying to find out what affects it, we've got to sort of sub in these different fractions or multiplication factors into our equation and sort of see what happens. So first one is the separation goes down by a third. So I'm just going to sub in down here, 1 over 3. The next one is it says the relative permittivity goes down by a third. So I'm just going to put a third next to this one here on top of my fraction. And the trickiest one is that it says the length gets increased to 3L. Now, when we're trying to see how much that affects the area, because it says they're square plates, each one of them is going to be side L, is going to be L big. So if we multiply it by 3L, actually what we're doing is multiplying it by 3L on both sides. So therefore we're going to have it going up by a factor of 9 because it's 3L times 3L on both sides. So putting all those factors in, we've got 9 and a third, which cancels down to 3 on top, and then we've got a third on the bottom, which is a third, which is divided by a third. Therefore, we get 3 divided by a third is 9 coulombs. That's how you do a question like that. And that's a bunch of multiple choice questions for capacitors. Hope you found it useful, and give it a like if you want more different topics for AQA A-level paper 2.